Okay, thank you. So our next speaker is Jesus, who has been talking a few times in the GoDev room about everything that has to do deeply within the language, and today he's going to talk to us about what's going on in functions. Round of applause.
Okay. Hello, everybody. Well, my name is Jesus. I'm software engineer at Marmos. I'm going to talk about squeezing a Go function. So what is optimization? I think it's important to know that optimization is not being faster or consuming less memory. It depends on your needs. So it's better fresh squeeze juice. Probably everybody will say yes, but it depends if you are looking for convenience or for something that lasts forever. So in that case, it's not the best option. Optimizing is about what you need and trying to address that. It's important to optimize at the right level. You can buy the best car, you can get an F1 car, and it's not going to be fast if this is the road. So try to optimize always at the upper level, because these kind of optimizations, the ones that we are going to see in this talk, are micro optimizations that probably are not the first place that you should be starting. So. Optimize what you need and when you need it. It's not about taking a Go function and try to optimize forever and try to make that run super efficiently and scratch every single nanosecond, because probably the bottleneck is no longer there. You have to search for the bottleneck, you have to optimize where the bottleneck is, and then look again if the bottleneck is still there. Because if it's no longer there, you are over-optimizing that function without much gain. So just take that into consideration. Optimizing is an iterative cycle, and you need to keep moving and keep searching for the bottleneck. Do not guess, please. Yeah, I know everybody have instincts and all that stuff, but guessing about performance is an awful thing, because there's so many things that comes into play that is just impossible. There's the operating system, the compiler, the optimizations of the compiler. If you are in the cloud, maybe noisy neighbor. All that stuff comes into play with performance. So you have to, you are not good at guessing, almost for sure, in performance. So just measure everything. The important thing here is try to measure everything and work with that data. Actually, is what probably the talk that is after the next one is about. So I will suggest to go there also, because it probably is a very interesting talk. So let's talk about benchmarks. The way that you measure performance in micro optimizations or micro benchmarks is through Go benchmarks. Go benchmark is a tool that comes with Go and is similar to the testing framework that comes in Go, but very focused on benchmark. In this case, we can see here an example to have two benchmarks, one for MD5 sum and one for SHA 256 for sum. And that's it. It's just a function that starts with benchmark and receive a testing.b argument, and that's this have this for loop inside. And that is going to do all the job to give you the numbers. And I show you now the numbers. If I run this with Go bench, we go test dash bench dot. The dot is a regular expression that means everything. So you can use like the Go test run a regular expression for only executing certain benchmarks. And here you can see that MD5 sum is around twice time faster per operation than SHA. So well, just a number. Is that important? It depends. If you need more security, probably MD5 is not the best option. So it depends on your needs. Another interesting thing is the allocations. One thing that you maybe have heard is about counting allocations. Counting allocations, why is that important? It's because every time we allocate something, when we talk allocation, we're talking about allocation in the heap. If every time we allocate something in the heap, allocating that is going to introduce an overhead. And not only that, it's going to add more pressure to the garbage collector. That's why it's important to count the allocations when you are talking about performance. If you are not worried about performance at that point, don't count the allocation. It's not that important, and you are not going to gain a massive amount of performance from there if you are not in that point there. Okay, let's see an example here. In MD5 and SHA SAMs, we have 0 allocations. So, well, this data is not very useful for us now. So let's use another thing. Let's open a file. Let's open a file thousands of times and see how it goes. Now I see that every single operation of opening a file, just opening the file, is going to generate 3 allocations. And it's going to consume 120 bytes per operation. Well, interesting. So now you know you are measuring things. You are measuring how much time it takes, how much time is gone in processing something, is gone in allocating things, how much memory is gone there. So let's talk about profiling, because once you, normally you do the profiling first to find your bottleneck, and then you do the benchmark to tune that bottleneck. But I'm playing with the fact that I already have the benchmark, and I'm going to do the profiling on top of the benchmark. So I'm going to execute the Go benchmark, I'm going to pass the mem profile, I'm going to generate the mem profile, and I'm going to use the pprof tool. The pprof tool is going to allow me to analyze that profile. In this case, I'm just asking for a text output, and that text output is going to show me the top consumers of memory in this case. And I can see there that 84% of the memory is gone in OS new file. Okay, let's see what happened. Okay, it's that file, but I need more information. Well, it's that function, sorry. I need more information. Actually, I kind of like this output, but if you don't like this output, you can, for example, use SVG, and you are going to get something like this that is very visual, and actually is kind of obvious that where is the bottleneck there. And in this case, again, is OS new file. If I go to the pprof tool again, and instead of that, I use the list of a function, I'm seeing here where is the memory going by line. And here I can see that in the line 127 of the file unix.go, I'm consuming the memory. Actually, there you see 74 megabytes. That is because it's counting all the allocation and aggregating all the allocations. It's not, every operation here is consuming only 120 bytes. Okay, the same with CPU profile. In this case, this is generating most of the CPU consumption is in syscall 6. I can see in SVG. This time is more scattered, so it's the CPU is consuming in way more places, but that's still the syscall 6 is the biggest one. So I'm going to list that, and I see some assembly code. Probably you are not going to optimize more this function, so probably this is not the place that you should be looking for optimizations. Anyway, this is an example of getting to the root cause during the profiling. Okay, this talk is going to be more by examples. I'm going to try to show you some examples of optimizations. It's just to show you the process more than the specific optimizations. I expect you learned something in between, but it's more about the process, okay? One of the things that you can do is reducing the CPU usage. This is a kind of silly example. You have a find function that have a needle and a high stack, and just go through the high stack and search for that needle and give you the result. This is looping over the whole string, or the whole slice. I'm going to do a benchmark. The first thing, I'm going to do the benchmark. I'm going to generate a lot of strings, and I'm going to do a benchmarks looking for something around in the middle. It's not exactly in the middle, but it's around there. And the benchmark is saying that it's taking nearly 300 nanoseconds. If I just early return, that is just a kind of silly optimization, it's not super smart or something like that, I'm going to save basically almost the half of the performance. This is because the benchmark is doing something really silly, and it can vary depending on the data that it inputs, but it's an optimization of just doing less. That is one of the best ways of optimizing things. Well, reducing allocations. One of the classic examples of reducing allocations is when you are dealing with slices. When you have a slice, for example, this is a common way of constructing a slice. I create a slice, I loop over this, generate a loop, and start appending things to that slice. Okay, fine. I'm going to do a benchmark for checking that. And it's taking 39 allocations and around 41 megabytes per operation. Okay, sounds like a lot. Okay, let's do it. Let's do this. Let's build the slice, but we are going to give an initial size of 1 million. And the time I just setting that. The final result is exactly the same, but now we have one allocation and we have consumed only 1 megabyte. And actually, if you see there, is around 800 microseconds, and here you have around, well, let me check, around 10 milliseconds. So it's a lot of time, actually, a lot of CPU time too. But you can squeeze it more. If you know that at compile time, if you know exactly the size that you want to have at compile time, you can build an array. It's faster than a slice, actually. So if I build an array, I'm now doing 0 allocations, 0 heap allocations. It's going to go in the stack or in binary somehow, whatever, but it's not consuming my heap allocations. And this time is 300 microseconds approximately. So an interesting thing if you know that information at compile time. Okay, another thing is packing. If you are concerned about memory, you can build this struct and say, okay, I have a Boolean, I have a float, I have a int32, and the Go compiler is going to align my struct to make it more efficient and work better with the CPU and all that stuff. And in this case, it's just adding 7 bytes between the bool and the float and 4 bytes after the integer to get everything aligned. Okay, I built a slice and initialize that slice, and I'm allocating 1 time because that's what the slice is doing, and I'm consuming around 24 megabytes per operation. If I just reorganize the struct, in this case I put the float at the beginning, then the int32, and then the Boolean, the compiler is only going to add 3 bytes. So the whole structure is going to be smaller in memory, and in this case, now is 16 megabytes per operation. So this kind of optimization is not going to save your day if you are just creating some structs, but if you are creating millions of instances of an struct, it can be a significant amount of memory. Function inlining. Function inlining is something that the Go compiler does for us. It's just taking a function and replacing any call to that function with the code that is generated by the function. I'm going to show you a very dumb example. I'm not inlining this function explicitly, and I'm using the inlined version that is going to be inlined by default by the compiler because it's simple enough. And then I'm going to execute that. I'm saving a whole nanosecond there. So, yeah, it's not a great optimization, to be honest. Probably you don't care about that nanosecond. But we are going to see why that is important later, not because of the nanosecond. I'm going to talk now about escape analysis. Escape analysis is another thing that the compiler does for us, and basically analyze our variables and decide when a variable escaped from the context of the stack. It's something that is no longer able to get the information from the stack or store the information from the stack and be accessible where it needs to be accessible, so it needs to escape to the heap. So it's what generates that allocations. And we have seen that allocations have certain implications. So let's see an example here. This is a not inline function that returns a pointer that is going to generate an allocation. This is something that returns by value. A value is going to copy the value to the stack of the caller, so it's not going to generate allocations. So we can see that in the benchmark that is saying the first version have one allocation and it's allocating 8 bytes, and the second one have 0 allocations. And actually you can see there, hey, it's one allocation and it's taking 10 times more to do that. 10 times more is, in this case, is around 12 nanoseconds. That is not a lot, but everything adds up at the end, especially when you are calling millions of times the things. Okay, and one interesting thing is escape analysis plus inlining. Why? Well, imagine this situation. You have a struct, a function that generates or instantiates that struct, and the constructor of that struct. Okay, the constructor returns me a pointer and do all the stuff that it needs. Okay, great. It is generating 3 allocations and is consuming 56 bytes per operation. Okay, what happens if I just move the logic of that initialization process into a different function? If we do that, suddenly the new document is simple enough to be inlined. And because it's inlined, it's no longer escaped. So it's no longer needed that allocation. Something that simple allows you to just reduce the number of allocation of certain types when you have a constructor. This is what I would suggest is just keep your constructor as simple as possible, and if you have to do certain complex logic, do it in an initialization function. Well, if that doesn't hurt the readability. Okay, let's see here. We have less allocations. We have now 2 allocations and 32 bytes per operation, and the time consumed is, you are saving 50 nanoseconds every time you instantiate that. So this is a good chunk. Okay. Well, this is optimization. Sometimes it's a matter of trade-offs. Sometimes you just can do less, like less allocations, less CPU work, less garbage collector pressure. All that stuff is things that can be done. But sometimes it's not about doing less. It's about consuming different kind of resources. I care less about memory, and I care more about CPU, or all the way around. So concurrency is one of that cases where you need to decide what you want to consume, because Go routines are really cheap, but are not free at all. So let's see an example with I/O. This is 2 functions that I created. One is a fake I/O that is going to generate some kind of I/O simulation by time sleep. And then you have the fake I/O parallel that receives the number of Go routines and is doing basically the same, but distributing all that 100 cycles between different Go routines. And I built a benchmark to do that using three different approaches. One is serial one, the no concurrency. The other one is concurrency using the number of CPUs in my machine, and the other one is using the number of tasks that I have. And because this is I/O, this is the result. I'm going to see that if I create 1 Go routine per job, the number of bytes per operation and the number of allocation is going to spike. But the time that is going to be consumed is going to be way lower. Actually, I'm able to execute 100 times this function using this one coroutine per job approach, and only 12 using one CPU per job. Because this is I/O. So let's see what happens if I do that with CPU. Using the CPU, this is to simulate some CPU load and using MD5 sum, and it's more or less the same approach as we saw in the fake I/O. The benchmark is exactly the same approach. We are using the number of jobs and the number of CPUs and using no coroutines. And here is interesting because if you use the number of CPUs and this is a CPU workload, that is what is going to do the best efficiency. You can see here that executing one coroutine per job is going to be even slower than executing that in serial. And actually, you have the worst of both worlds. You have plenty of allocations, plenty of memory consumption, plenty of time consumption, and you are not gaining anything. In the case of CPU, you are consuming more memory, you are consuming more memory, and you are getting better CPU performance because you are basically spreading the job all over your physical CPUs. And the serial one is just doing everything and is using only one core of your CPU. So whenever you want to optimize using concurrency, you have to take in consideration what the kind of workload that you are using. Is the CPU workload? Is it I/O workload? Do you care about memory? Do you care about CPU? What do you care about? So well, that's the whole idea. I just want to explain that all this is about measuring everything, measuring all these, doing all these benchmarks, doing all these kind of experiments to see if you are getting improvement on the performance and iterate over that. That's the main idea. I show some examples of how you can improve things, and some of them can be applied in general basics, like using try to keep constructors small, or using the constructors for slices when you know the size and things like that. Some references. Efficient Go is an O'Reilly book that is really interesting if you are really interested into efficiency. Bartolome Plotka wrote that book and actually is going to give a talk after the next one. So I'm almost sure it's going to be super interesting. High Performance Workshop from Dave Cheney. There's a lot of documentation about that workshop that Dave Cheney did, and it's really interesting also. The GoPerf book is a good lecture also. An Ultimate Go course from Ardon Labs is also an interesting course because it's giving you a lot of foundation, and the course cares a lot about hardware sympathy and all that stuff. Well, some Creative Commons, all the images are Creative Commons, so I put the reference here because it's Creative Commons. And thank you. That's it.
Thank you.